Good evening, everyone. So, in this session, we'll be seeing problems from week 4 assignment, and also along with that, we'll also see the problems that are to be given as practice problems or non-graded assignment. The first problem for today's session is that uh, basically, this is the Computational Fluid Dynamics problem solving session number 4. The course instructor is Professor Srinivas Jayantri from IIT Madras. So we'll move on to today's session. So in this week, the first problem involves around a case. So we'll see what the case is, and then we'll see the problem. What are all the questions that are asked from this? So first, initially, it is given that a catalytic flow reactor having dimensions L into W into H such that L is very much greater than W and W is very much greater than H. Gaseous mixture of CO and H2O enters the reactor through plane A and leaves through plane D. Catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 times length and 0.75 times length from the inlet. The reactor is preheated through the top and bottom walls over the distance between planes A and B. So it is before solving any problem, we must understand what the problem is about and identify what the questions that could be asked from the problem. So initially it is given that this is a catalytic flow reactor. So basically this week's session, this week's content from the CFD course is basically about chemical reactions, mass transfer, heat transfer. Previously, we saw a flow through triangular duct, rectangular duct, and so on. So, in the next step, we are moved toward the heat transfer and mass transfer problems. So, basically, we are also we have also been seeing how chemical reactions problems can be solved through CFD. So basically it is given that it is a catalytic flow reactor having dimensions L into W into H such that L is very much greater than W. So this is one is a catalytic flow reactor with dimensions L and this one is height is very much smaller, and this one is width and this one is L. Sorry. So it can be seen that L is very much large and width is comparatively smaller than length, and height is very smaller. So these are the dimensions given for this problem, and it is given that gaseous mixture of CO and H2O enters through the reactor through plane A and leaves through plane D. So basically they have announced or marked few planes. This one is plane A, B, C and D. So the reactant mixture containing carbon monoxide and water enters through plane A and leaves through plane D. Catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 times of L and 0.75 times of L. So it is given that the red portion is catalyst. So at the bottom of the bottom wall is coated with catalyst between the planes B and C. So the planes B is exactly at the middle, and C is at the center of planes B and D. At the midpoint between planes B and D lies the plane C. So then it is given that the reactor is preheated or cooled through the top and bottom walls over the distance between planes A and B. Between the planes A and B, it is given that the reactor can be preheated or cooled depending on the requirement between the bottom and the top walls. So these are all the things that are mentioned in this problem, like the dimensions of this case is given, where the height is very smaller and the width is comparatively larger than height and length is very larger. And from the plane A, gaseous reactants like carbon monoxide and water mixture enters and it leaves through plane D. Whereas between plane B is at the midpoint of planes A and D, it is exactly at the midpoint, and plane C is at the midpoint between planes B and D. So between the two planes B and C, it is coated with catalyst. So and it is given that between planes A and B, it is either preheated or cooled depending on the requirement through the top and the bottom walls. So these are all the conditions given in this problem. We will see what are the questions. So they have given more explanation for this case. We need to solve for the flow in reactor in which the following water gas shift reaction is taking place. So basically carbon monoxide plus water gives carbon dioxide plus hydrogen. This reaction is mildly exothermic and is to be carried out in a targeted temperature range based on the desired output condition. All the species are in gas phase, but the reaction is catalytic. In the reactor, the catalyst is coated on the bottom wall between planes B and C, which are at a distance of 0.5 times L and 0.75 times L respectively. We wish to use the length of the traverse between planes A and plane B for preheating or even cooling if the reactants are at too high temperature to begin with. We need to find out how much conversion takes place, that is how much of the carbon monoxide coming through the inlet gets converted to carbon dioxide and to the production of hydrogen. We want to find this out using CFD simulation. Assume steady laminar flow and answer the following questions. So basically the reaction that is taking place in this is carbon monoxide plus steam gives carbon dioxide plus water. All the reactants in this are in the gaseous phase. So it is given that the following gas shift reaction is taking place in the reactor where carbon monoxide and water gives carbon dioxide plus hydrogen. This is given that the reaction is exothermic. So it should be carried out in the targeted temperature range based on the output composition. So depending on the temperature range, the output composition varies. All the species are in gaseous phase, but the reaction is catalytic. The reaction is catalytic. So basically the catalyst is coated between planes B and B and C, which are at a distance of 0.5 times length and 0.75 times length, as we have seen in this figure, where the red portion they are coated in between is the catalyst. And then it is given that we wish to use the length of traverse between plane A and B for preheating or even cooling if the reactants are at too high temperature to begin with. So it is given that if the reactants are at too high temperature, it is cooled or it is preheated depending on the requirement. Between planes A and B, the preheating or cooling is taking place. So from this reaction, it is required that we find out how much conversion takes place, how much of the carbon monoxide coming through the inlet gets converted to carbon dioxide and to the production of hydrogen. We want to find these out using CFD simulations, and it is given that we can assume the flow to be steady laminar flow, and we should answer the following questions. These are the cases given in this. So since we are dealing with mass transfer, heat transfer and chemical reactions in these in this week tutorial, before moving on to the questions, we'll just quickly go through what are all the equations that needs to be solved. So the first equation is basically continuity equation, where it is given that dou rho by dou t plus del dot rho times u is equal to 0. This is continuity equation or mass conservation equation, and the momentum conservation equation states that dou u by dou t plus del dot u times u is equal to nu times del dot del u plus gravitational force minus 1 by rho del p, that is the pressure force. This is due to the convective term and this is the diffusive term. And energy conservation equation is given in this form, where it is given that dou T by dou T plus del dot U times T is equal to K by rho Cp del dot del T plus mu by rho Cp times phi V plus QR by rho Cp. Cp is the heat capacity, K is the thermal conductivity, and rho is the mixture density, and phi V is the viscous dissipation term, and QR is the heat produced in the system. And in addition to this, when we are dealing with mass transfer or chemical reaction, when it is involved, we need to account the species conservation also. So it is basically dou times of rho yi by dou t plus del dot rho times uyi is equal to del dot gamma times del yi plus si. Basically yi here is the mass fraction of the individual terms. So we need to know the species fraction in this system to get to know the species conservation. Then only we can use these equations in CFD to solve this, where SI is the rate of formation of any species, and this term comes from the mass flux equation or mass conservation equation. So moving on, we'll see what are all the questions that are asked in this. So the first question that is asked is, how many mass conservation equations do we need to solve? So basically it is asked that how many mass conservation equations we need to solve in this system where it is given previously. So we'll see what are all the options that are present for this question. The first one is only the one for CO, carbon monoxide, and the second one is only those for carbon monoxide and carbon dioxide, and option 3 any three species conservation equation and mixture continuity equation, and none of the above. So basically, how many mass conservation equations do we need to solve? So we'll go back and we'll see what are all the governing equations that were present. So the first one is the continuity equation. So this is mass conservation equation, and this is this is momentum conservation equation, this is energy conservation equation, this is species conservation equation. This gamma is nothing but diffusivity term. So basically, like, we have one continuity equation and species conservation equation that comes under the mass conservation term. How many mass species conservation equation would we be having? We would be having 2 for the reactants and 2 for the products, because carbon monoxide plus water was giving carbon dioxide plus hydrogen. So from this, it is like 4 species conservation equation. When it is 4 species conservation equation, if it is put together, we'll get the continuity equation. So in that case, we need not solve for 4 conservation equation. Rather, if we go for 3 species conservation equation and 1 mixture continuity equation, that would be sufficient. If it is only for one for CO, carbon monoxide, it doesn't make any thing, because with only one species conservation for one of the reactants, it is not going to give the solution, and also with only one for one reactant, that is carbon monoxide, and one for product, also it would not be giving us the answers. In a similar fashion, with any three of the species conservation equation and mixture continuity equation, we can solve the problem, and it is not none of the above. So we'll see the answer to this question. It is answer is option 3, that is any three species conservation equations and mixture continuity equation. So basically, this is the solution to this. The number of species in this problem is 4. that is carbon monoxide, carbon dioxide, and hydrogen and water. So when everything is put together, it is 4 species involved in this reaction. And continuity equation, that would be 1. So basically the species conservation equation that needs to be solved is ns minus 1, where ns is the number of species. So basically it would be 4 minus 1, 3. So 3 plus 1 continuity equation, so that would give 3 plus 1, 4, or ns minus 1 plus 1, that would be total number of mass conservation equations would be 4, or ns number of species. So basically the answer is ns minus 1, that is 3 species conservation equation, and mixture continuity equation, that is 1 equation. Or together, everything put together, the number of equation would be 1. So I hope it is clear. We'll now move on to question 2. Is there any doubt from the audience? No, we'll just see the question 2. So, which of the following statements is true about chemical reactions? So, in this problem, it is a series of statements is given, and we need to identify which of the following statements are true. The rate of reaction needs to be specified. The stoichiometric coefficient of the reactions are sufficient to calculate the reaction rate. The rate of reaction need not be specified, as it can be calculated using thermodynamic equilibrium. Kinetic parameters of the reaction rate needs to be specified. So, when dealing with chemical reaction, few things are needed to be looked into. That is, new terms come in picture, like species conservation equation, and since it is associated with temperature changes, energy conservation equation also additionally come into picture. So mainly when we are dealing with chemical reaction, rate of reaction need not be specified in the governing equation. If the constants and other terms in the rate of reactions are known, so the rate of the reaction need not be known. Other parameters like values we should know. So it is not required, and it is given that stoichiometric coefficients of the reaction are sufficient to calculate the reaction rate. Stoichiometric coefficients of the reaction are required, but it is not sufficient to calculate the reaction rate. I mean, it is not sufficient. The rate of reaction need not be specified, as it can be calculated using assuming thermodynamic equilibrium. Basically, this statement is also not true. Next option, it is given that the kinetic parameters of the reaction rate needs to be specified. So obviously, when we are solving things in governing equation, kinetic parameters of the reaction should be specified. So kinetics of the reaction, like stoichiometric coefficients, order of reactions, and constant in rate equation, all these together need to be known when we are dealing with chemical reaction. So the kinetic parameters of the reaction rate needs to be specified. So this covers everything. One alone or is not sufficient. So basically, stoichiometric coefficients, order of reaction, constants in rate equation, everything needs to be known to calculate the system. So which of the following statements is true about the chemical reaction? It is kinetic parameters of the reaction rate needs to be specified. So when we are just seeing the governing equation, we'll see this one more time. So basically it is in species balance, we'll be using the SI term, where it is the rate of formation of species. So we obviously in this term we'll be using solving for the chemical reaction. There we would be needing the kinetic parameters like stoichiometric coefficients, order of the reaction, and also the various constant constants that are present in the rate equation. So answer is option 4. Kinetic parameters of the reaction rate needs to be specified. So which of the following statements is true about the chemical reaction? It is kinetic parameters of the reaction rate needs to be specified. I hope this is clear. We'll move on to question 3. Terms related to the reaction rate would appear in which of the following balance equations? So it is given that mixture continuity equation, mixture momentum balance equation, mixture energy balance equation. It is given, 3 of this is given: mixture continuity equation, mixture momentum balance equation, and mixture energy balance equation, where it is asked that terms related to the reaction rate would appear in which of the following balance equations. So in options, out of these three equations, which of the following balance equation contains the reaction rate? Terms related to the reaction rate. The question, options are 1 and 2, 2 and 3, 1, 2 and 3, or none of the three equations. So we'll first see the governing equations and then we will see terms related to the governing equations. So it is not present in the continuity equation, it is not present in the momentum conservation equation or energy conservation equations. It is present in the species conservation equation. So the answer to this question would be none of the three would be the correct answer. So we'll move on to question 4. In figure 1, the thermal boundary condition over the top wall between planes A and B can be temperature specified, heat flux specified, heat transfer coefficient specified. In figure 1, that is the problem statement or case that is under consideration for us. In that case, it is asked that thermal boundary condition needs to be specified because it is this problem is involving heat transfer. So it is asked that in figure 1, the thermal boundary condition over the top wall between planes A and B can be temperature specified, heat flux specified, or heat transfer coefficient specified. So basically boundary condition comes under two types. One is Dirichlet boundary condition, another one is Newman boundary condition. So when we are specifying the values for the variables, that is known as Dirichlet boundary condition. And if we are specifying the flux values or derivative values for the derivatives, that is known as Newman boundary condition. Or there would be problems where we would be specifying both of these. So it is given that temperature specified, heat flux specified, heat transfer coefficient specified. So obviously it would be like temperature can be specified to solve this problem, or heat flux can also be specified to solve this problem, but heat transfer coefficient need not appear in the thermal boundary condition. It would be obtained as a solution of the thing, but we need not mention it in the thermal boundary condition. So now we'll see what are all the options that are available for this problem. It is 1 and 2 for option 1, and option 2 it is 2 and 3, option 3 it is 1 and 3, option 4 it is 1, 2 and 3. So option 1 is right because it is mentioned 1 and 2, whereas 3 is false. So option 2, 3 and 4 all are having option 3. Therefore, the correct answer to this problem would be 1 and 2. The correct answer is option 1, where it can be temperature specified, or it can be heat flux specified, or it can be both, but it would not be heat transfer coefficient specified. That is the thing that is that is what we should understand from the energy conservation equations or energy balance equations. So I hope this is clear. If there is any doubt, please let me know. So yeah, we'll see. We'll move on to the next question. That is question 5. In figure 1, If the reaction rate is very high, the boundary condition for the carbon monoxide species conservation equation at the bottom of the reactor between planes B and C is. So it is asked that if it is assumed that the reaction rate is very much higher, so what would be the boundary condition equation for carbon monoxide concentration species uh, concentration of carbon monoxide species at the bottom of the reactor between planes B and C. So we already saw that the reactor is like this, this. Sorry, way it is like a plane where plane A is the center and plane B and C are at the B is at the exact midpoint and C is halfway between planes. C is C is half C is halfway between planes C and D. Sorry, B and D. So it is asked that if the reaction rate is very high, the boundary condition for carbon monoxide would be at the bottom of the reactor between planes B and C would be. So we'll see what are all the options that are available. First one is concentration would be 0, and second would be concentration gradient would be 0, and third would be concentration gradient is equal to constant. So basically the problem statement was given that carbon monoxide and water enters through plane A and leaves through plane D. B is at the midpoint of the planes. Between planes B and C at the bottom of the reactor, catalyst is coated. So obviously there would be no carbon monoxide present. So the answer to this question would be concentration is equal to 0. So we'll see what are all the options that are given to identify the answer. In first it is given that option 1, and in second it is given option 2, and third is option 3, and fourth is boundary condition is not required. Basically it is that concentration is 0. Other things like concentration gradient is 0 or it is constant does not come into picture, because it is like at the bottom of the reactor between planes B and C the catalyst is present. So the boundary condition obviously does not come with carbon monoxide. So concentration is equal to 0. So the answer to this question is option 1. So answer is option 1. So we'll move on to question 6. Which of the following statements is true about the expected temperature variation along the center line of the reactor if the reactants enter at lower than the targeted temperature? So it is given that, it is the question clearly specified that is temperature should be, that is an exothermic reaction and temperature condition should be maintained along the targeted temperature. So preheating or cooling between planes A and B would be carried out depending on the requirement, or how to say, depending on depending on what the situation demands. So basically in this question number 6 it is asked that which of the following statements is true about the expected temperature variation along the center line of the reactor if the reactants enter at lower than the targeted temperature. So if it would be preheated and its temperature would be rising, that would be the answer, because expected temperature variation would be that like till it attains the targeted temperature, that would be rising. So we'll see what are all the options available. The first one, it is given that temperature decreases monotonically in the flow direction, And in second option, it is given temperature increases monotonically in the flow direction. Temperature increases in the first half and then decreases. And temperature increases up to plane C and then remains constant. So, we have seen that initially that thing that is present is plane A. And the next thing that is present is plane B at the midpoint. I mean, plane A is at the initial one and plane D is the last one, where the reactants enter through plane A and leaves through plane D, with a plane B at the midpoint and plane C at midpoint between planes B and D, where catalyst is coated between planes B and C. So obviously the reaction would be taking place at max between planes B and C, where catalyst is present. So at that till that range, we expect the temperature to be maintained. Uh, Temperature variation would be present along. So the answer to this question would be temperature increases up to plane C and then remains constant. So till C, the whereas between A and B, it would be heated, preheated because of the like it was mentioned that depending on our requirement of to maintain it along the targeted temperature range, whereas if the reactants are at higher temperature, it would be cooled down, or else if it is below there, it would be preheated. So between planes A and B, initially it would be preheated, so the temperature would be increasing, whereas between planes B and C, the reaction would be exothermic, so again it would be increasing. In that range, it would be maintained at constant, sorry, it would be increasing from planes A and C, that is up to plane C the temperature would be increasing, after which uh, the temperature would remain constant. So the answer to this question would be option 4. So answer is option 4. So initial, like what are the options that were available are like temperature decreases monotonically in the flow direction, temperature increases monotonically in the flow direction. Like it does not completely increase or decrease in the flow direction. Rather, it increases up to a certain point, after which it remains constant. And temperature increases in the first half and then decreases. First half means up to plane B, whereas that is not the case, because since it is an exothermic reaction, there is no point, no chance that the temperature would be decreasing afterwards. So the answer to this question is temperature increases up to plane C and then remains constant. This is question 6. We'll move on to question 7. The viscous dissipation term that appears in energy conservation equation is absent in inviscid flows, incompressible flows, non-Newtonian flows, in flows with shocks. So basically it is asked that viscous dissipation term that appears in energy conservation equation would be absent in which of the following flows. So the first option is inviscid flows. Inviscid flows where the viscosity effects would not be there. Those are known as inviscid flows. And in the second option, it is known as incompressible flows where density changes would not be there. And non-Newtonian flows, those fluids that does not obey Newton's law of viscosity, or there would the viscosity, there would not be linear relation between stress and shear rate, and inflows with shocks. In like flow, there would be like a discontinuity in the flow field in those flows. So those are known as this. So we'll see how the answer to this question is inviscid flows. We'll see how we can say it is inviscid flows. So basically, we'll see what are the inviscid flows first. Inviscid flow are like where viscosity effects would be neglected. So basically, inviscid flow assumption means physically that viscous shear and normal stresses are negligible. Thus, all of the viscous shear stress terms on the force side of the momentum equation drops out, as well as the normal stresses due to viscosity. So, in inviscid flow assumption, this is an assumption case, like where physically the viscous shear and normal stresses are very low and they are neglected. In that case, all of the viscous shear stress terms on the momentum balance equation, they drop out, and also the normal stresses due to viscosity, they drop out. So basically, it is asked that viscous dissipation term, that is the phi v term, phi v that is present in the energy conservation equation, that would be absent in which of the following flows. So basically, when there is inviscid flows, then viscous shear and normal stresses are negligible, and so these terms drop out. When you are, this is like assumption case, but when we are dealing with real heat transfer problems, when you are dealing with real heat transfer problems where the heat fluxes are strong and then you have a temperature variation associated with the flow, and all those things are very strong, the contribution of viscous dissipation of energy is usually very small and it is neglected. Uh, so, um, um, so when it is like temperature variation is associated with the flow and the heat flux are strong, like viscous dissipation would be effect would be small and it would be neglected. But when velocity induces temperature variation, that because of fluid flow, if temperature variation is affected or temperature variation is caused, uh, that would be the more practical problems, like so in cases where we are dealing with highly viscous I'm sorry. So this would be the case like velocity induced temperature variation would be practical case. Normally when we are dealing with highly viscous fluid like glycerol, petroleum, etc., viscous dissipation of energy arising out of work done by viscous forces should be considered. In other cases, it can be neglected. That is, this is the energy balance equation. That is rho Cp dou T by dou T plus rho Cp del dot Ut is equal to K del square T plus mu phi V. The phi V is the viscous dissipation term. When studying mixture of highly viscous fluid using an impeller, we would have to consider this viscosity as it would generate a sufficient amount of local dissipation and local increase in temperature, which may have a consequent large change in viscosity, which would then be coming into momentum equation, and that could change the velocity field. So when highly viscous fluids are considered, like consider a case where one of a highly viscous fluid is mixed using an impeller. The viscosity, if it is very high, there would be a very much large energy required, and the local dissipation would be very high, and also the temperature increase in that case would be very large. So this large change in viscosity that would then come into picture in the form of momentum equation, and there it would change the velocity field. So in those cases, we need to consider the phi v or the viscous dissipation term. But in other case, normal case like very light fluids, lightly viscous fluids or liquids, gases are considered, this term could be neglected. That is essentially from the thermal conservation equation or temperature energy conservation equation. So in when this would be considered lightly viscous fluids would be inviscid fluids. So the answer to this question is inviscid flows, where inviscid flow means that physically the viscous shear and normal stresses are negligible. In those cases, when the effect of viscosity is very high, very low, uh, thereby it would be it can be assumed that viscous dissipation terms would be neglected. So just a minute, it is like I mean, here it should be like it won't be neglected in real heat transfer problems. So, so in all these cases, it would not be considered, whereas when light fluid is considered, we can neglect those terms. But when highly viscous liquid is considered, we should not neglect viscous dissipation force. That is when we are mixing, consider the case where we mix a highly viscous liquid, there the energy dissipation would be very high, and although the local temperature increase because of that would be very high. In those cases, those terms cannot be neglected, but it should be included. But in cases where light viscous fluids are used, we can neglect those terms. So basically, in viscous flow term, we can neglect the viscous dissipation force. In other things, we cannot neglect the effects of viscous dissipation force. So we'll move on to question 8. In question 8, it is asked that which of the following is already included in the energy equation that we solve along with Navier-Stokes equation for flows with heat transfer. So which of the following is already included in the energy equation that we solve along with Navier-Stokes equation for fluid flows with heat transfer? Convective heat transfer, radiative heat transfer, and boiling heat transfer. All of the above require additional modeling. So basically, when which of the following heat transfer equation is included in the energy equation that we solved along with Navier-Stokes equation for fluid flows with heat transfer? When we are dealing with heat transfer problems, basically we solve continuity equation and momentum conservation equations. Along with that, we also solve the energy balance equation or energy conservation equations. So in this energy conservation equation, basically, what are all the heat effects? What are all these things that are already included in the energy equation that we solved? So basically, this is the energy equation where this denotes the change in the temperature, and this would be the del dot ut. This would be due to convective term, that is flow, and this would be the diffusive term. So basically the uh, heat transfer due to the fluid flow is basically included in this term. That means that convective heat transfer is included in the energy equation that we solve along with Navier-Stokes equation for fluid flows with heat transfer. Radiative heat transfer, when radiation effects are considered with, that is when we are dealing with high temperature change problems, radiation effects should be considered, but in most of the cases, the things would be very much complicated with radiation. Therefore, we do not include the radiative heat transfer in. We have not included the radiative heat transfer equation in these things. And the next is boiling heat transfer. Boiling heat transfer, it is that phase change is occurring because of this. So additionally, equations should be included when we are dealing with boiling heat transfer, or even like cooling, like phase, whatever the phase changes are involved, we should be using additional heat transfer equations. But in normal energy balance equations that we solve along with the Navier-Stokes, we use convective heat terms are already coming into picture. Say, like condensation, boiling and all requires separate modeling equations. And the radiative effect would be obviously dominating at a higher temperature. Uh, so like it is not used in these energy balance equation. So the convective heat transfer equation is only involved. And on fourth option, it is given that all of the above require additional modeling. Not true, because convective heat transfer is already included in the energy equation that we solve along with the Navier-Stokes equation. So the answer to this question is option 1, that is convective heat transfer is included in the energy equation that we solve along with Navier-Stokes equation for flows with heat transfer. Um, So it is given that the solution of energy equation with appropriate boundary condition takes account of convective heat transfer for the fluid. There is no need to simulate convective heat transfer as it is already included in the governing equation for the energy, because the advection term here is only place where velocity is coming and it takes care of the convective heat transfer. This is a constant property form for the energy conservation equation, and it is given that this is the advective term. Advective term here is the only place where velocity is coming into picture, and this term basically takes care of the convective heat transfer. So it is given that the solution of energy equation with appropriate boundary condition takes account of heat transfer for the fluid. So this equation along with appropriate boundary conditions includes the convective heat transfer. So basically no need to simulate convective heat transfer as it is already included in the governing energy equation. With this advective term including the effects of fluid flow with velocity coming into the picture, thereby the convective heat transfer is accounted in this equation. The question answer to this question is so the following is already included in the energy equation that we solve along with Navier-Stokes equation. For flows with heat transfer, it is convective heat transfer. We'll just take a 5 minutes break before starting with the next few problems. So we'll get back to the session. So I would like to make a point over here where when we were dealing with this one where viscous dissipation term that appears in energy conservation equation is absent in inviscid flows. So basically when we are dealing with real heat transfer problems where heat fluxes are strong and you have a temperature variation associated with the flow, and also those things are very strong contribution of, and also those things are very strong, the contribution of viscous dissipation energy is very small, so it is neglected. But generally if any practical cases of interest where velocity induced temperature variation and heat fluxes associated with conduction, their viscous dissipation effects are neglected. But when we are dealing with highly viscous liquid like glycerol, petroleum, crude oil, etc., viscous dissipation of energy arising out of work done by the viscous forces should be considered. So there was a mismatch in this sentence previously, so that sentence I have corrected. Uh, so basically when we are dealing with real heat transfer problems where the heat fluxes are strong and we have a strong temperature variation associated with the flow, and all those things are very strong, the viscous dissipation energy is very small, it is neglected. But more general terms, if for any practical case of interest, if it is velocity induced temperature variation and heat fluxes, we can neglect the viscous dissipation effects. But when we are dealing with highly viscous liquids like glycerol, petroleum, crude oil, like viscous fluids, we need to consider the work done by the viscous forces, so it should be considered. So we'll continue with the problems. Here we saw that which of the following equation is already included in the energy equation that we solve along with Navier-Stokes equation. So here we found out that convective heat transfer term is already included in the energy equation that we solve along with the Navier-Stokes, whereas boiling and condensation and all requires additional modeling, and radiative heat transfer is a vast topic to be studied altogether. So the answer is option 1. So we saw how this is like the advective term that where velocity is coming into picture and it is taking care of the convection heat transfer. So we'll move on to question 9. In question 9, it is asked that well-posedness of an initial value problem means. Um, we are having few options. Having the guarantee of a solution, having a unique solution, having a solution that is responsive to changes in initial and boundary conditions. Yeah. So basically, well-posedness, what for an initial value problem, what does it mean is that for the problem with all those conditions, there should be an solution. The solution should be guaranteed. That thing should be there. And the next thing is unique solution should be there. It does not mean that once the solution is guaranteed, it is over. No. The solution should be unique. And it is given that the solution, having a solution that is responsive to changes in initial and boundary conditions. So if there is any small changes occurring in the system, the problem should be in a position so that the solution should automatically respond to that change. Well-posedness in general means this. Altogether, all of these things should be there in the problem for us to solve an initial value problem. That is what is meant over here. So basically, when we are solving any problem, we look to that so that there is well-posedness. That is a partial differential equation that is we are solving. would be in general having an initial and initial and boundary conditions, so that we can use those things to formulate an appropriate mathematical problem. That is, we put together all the conditions and get the mathematical problem. So the that is that like we are having a system with numerous things that are discretized. I mean, we have used the governing equations to solve the system, and for that we have discretized, and we will be having initial condition and the boundary conditions. So all these would now be in the form of a mathematical model or mathematical problem. For this solving of the mathematical problem, we expect it to be having a unique solution. I mean, first we expect it to guarantee a solution, and we expect it to have a unique solution, and the solution should be such that it should respond to changes in the initial and the boundary conditions. So these are all the things that we expect from the mathematical problem. So that is what it is means by well-posedness. Well-posedness of an initial value problem means having the guarantee of a solution. This is true. Having a unique solution. This is also true. Having a solution that is responsive to changes in the initial and the boundary conditions. This is also true. So we'll see what are all the options given for this problem, and it is given that 1 and 3 uh, 1 and 3 are true, but option 2 is also true, and 2 and 3 same way. Option 1 is also true along with 2 and 3. 1, 2 and 3. So answer to this problem is option 3, that is 1, 2 and 3, and none of the above. This is obviously false because all three options given are true. The answer to this problem is option 3. So we'll move on to question 10. In question 10, it is asked that boundary conditions over the entire boundary may not be needed for what type of problem? So it is asked that parabolic, elliptic, hyperbolic, and none of the above. And the answer to this is option 3, hyperbolic. So we'll see how the answer is hyperbolic. Before seeing that, we'll see what are parabolic, elliptic, and hyperbolic. Boundary conditions over the entire boundary may not be needed for what type of problem? So, hyperbolic equations. So basically, what we try to do in CFD is, when we are having few equations like quasi-linear equations, we would be try to solve them. For that, we need the initial and the boundary conditions. So there are certain restrictions that we place in determining them from the nature of the equations. So the generally we have a set of partial differential equations. The partial differential equations can be classified into parabolic, elliptic, hyperbolic, or even mixed type, depending on few conditions. So basically, when there is a quasi-linear equation, uh, there are few like based on Cramer's rule or something. We classify the hyperbolic. I mean, we classify those partial differential equations. I mean, we first of all we write the equations, and we simplify those equations into a form where depending on b square minus 4ac, I mean, we'll just get it into a simplified equation form, and from that we classify those equations into hyperbolic, parabolic, elliptic, or mixed. These solved equations in general have a different nature. For example, this is hyperbolic equation. So these I mean, we can put together in this, like characteristic curves will be drawn. characteristic curves are nothing but along those lines, like if we can draw number of lines along this from this point P. But when we are drawing lines along the characteristic curves, the it would be indeterminate, or the determinant would be zero in that direction. So from that we would be getting the characteristic curves. So when we are getting the characteristic curves and we are extending it to the this boundary in both the left and right, so we will get a few data, that is A and B. So initial data along y-axis upon which P depends on. So basically, this is the region of dependence. So and this is the region influenced by point P. So this is the characteristic curve, that is P in this direction, and this one. This is right running characteristic and left running characteristic. So when we are extending it, we'll get a few, smaller domain. This is known as initial data. This one is the initial data points along the y-axis upon which, the value at P initially depends on this region A to B. Between Y and A, or between B and C, it does not influence the P, point P, from which it value extends. So this is known as region of dependence. So from all these values would be influencing P, and this would be the region influenced by point P, that is known as region of influence. This is region of dependence and this is region of influence. So basically for this equation we need only a set of few values. The initial condition should be from this. If we are considering an initial value problem, the initial values along the boundaries would, we need not get all these like between B to C or between A and Y would not give us correct initial conditions to determine the point P or moving further. So this only this data is required. So hyperbolic requires only a shorter span of data. So moving on, this is parabolic equation. Parabolic equation is that this is known as region of dependence and this is region influenced by P. So basically this is the initial data line, and it would be like boundary conditions are known in all these domain. In the total domain, from this we would be knowing the boundary conditions. So whereas in previously only like a few data was determined, that is not the case in P. All these region influences the all this region values. So boundary condition can be taken from any of these points, that is parabolic equation. Then moving on, this is elliptic equation. In elliptic equation, we does not have any limited values. So the boundary condition, basically in parabolic equation, the if we are taking it in this direction, and this is sorry, this is time and this is x values. So basically from we can use anything in this domain till the point P for parabolic, whereas for elliptic all the points would be influencing P. So this is known as future values would also be considered in the elliptic equation. So in for a hyperbolic equation we had only a few data points. We were not using all. Here we were using all the boundary conditions, and similarly for elliptic also we were using, we could use all the boundary conditions, but for hyperbolic only a few, this region of dependence only should be accounted when considering the boundary conditions. That is, we should be using only points within this region for calculating the P. So that is why the boundary conditions over the entire boundary may not be needed for what type of problem. The answer to this is hyperbolic. Hyperbolic does not need the entire boundary. Boundary conditions over the entire boundary. Only a small portion, of region influences all other things. Whereas in parabola and elliptic equation, all the boundary conditions could be used. So these are all the questions that were asked in week 4 assignment problems. So now we'll move on to week 4 practice problems, so that they have given a reactor setup in this week 4 practice problem. So it is a case study where it is given that once again, case to solve, we need to solve for the flow in the reactor in which CO is getting converted to carbon dioxide with the production of hydrogen, water gas shift reaction on a catalyst. So this was the same reaction that we studied. I mean, we solved the problems for week 4 assignment, where carbon monoxide reacts with water to give carbon dioxide and hydrogen. We need to solve for the flow in the reactor in which carbon monoxide is getting converted into carbon dioxide with the production of hydrogen. Let us assume a simple configuration for this reactor. Let us assume a simple configuration for this reactor. The multi-gas mixture flows through a rectangular channel. Due to its reaction, its composition changes from inlet to the outlet. The top and the bottom of the walls are coated with the catalyst, and the two side walls are used to heat up the gas to the desired temperature of 200 degrees Celsius. For a given flow rate of air with a given concentration of 4 gases, for given side wall heat flux and a given catalyst surface area, we wish to calculate the percentage conversion of carbon monoxide to carbon dioxide by the time it reaches the channel length. We want to find this out using CFD simulation, assuming steady laminar flow and first order reaction kinetics for the reaction. Assuming all these things, answer the following questions. So we'll just go through what are all the things that are given in this problem. So the first thing is, it is a water gas shift reaction between carbon monoxide and water and carbon dioxide plus hydrogen. The multi-gas mixture, that is carbon monoxide and carbon dioxide, enters through the rectangular channel. Due to the reaction, its composition changes from the inlet to the outlet. So basically the reaction is entering in this side and leaving it, we are assuming leaving in this side. The catalyst is coated in the top and the bottom walls. So basically the reactant concentration and the product concentration vary between the inlet and the outlet. Multi-gas mixture flows through a rectangular channel. Due to its reaction, composition changes from inlet to outlet. The top and bottom walls of the channel are coated with catalyst. So, top and bottom walls are coated with the catalyst, and two side walls are used to heat up the gas to the desired temperature of 200 degrees Celsius. So this side wall and that side wall are used to heat up the gas. The reaction mixture is needed to be maintained at a desired temperature of 200 degrees Celsius. For that purpose, we are using heating in the two side walls. For a flow rate of given air with a given concentration of 4 gases for given side heat flux. So it is basically flow rate of air would be given, and concentration of 4 gases, that is 2 reactants and 2 products, for given side heat flux and catalyst surface area is given. The percentage conversion of carbon monoxide to carbon dioxide is required by the time it reaches the end of the channel. So this is needed to be studied using CFD simulation. So when assuming steady laminar flow and first order kinetics, what would be the solution to the following problems? So in question 1, it is given that which of the following needs to be specified for statements is which of the following needs to be specified for statements is true about the chemical reaction. So there are few statements given regarding the problem about the chemical reaction. So we need to identify which of the following statements are true. So the first statement is, okay, sorry. It is asked that which of the following should be specified to solve the problem involving chemical reaction. Rate of the reaction, reaction kinetics, and the heat of the reaction. So we'll see what are all the options that are given. 1 only, and it is option 2 is 2 only. Option 3 it is 1 and 3. Option 4 it is 2 and 3. So this is the problem involving chemical reaction and also heat transfer is involved. So basically we'll be solving 4 set of equations. That is one continuity equation, 3 momentum conservation equations because the problem is 3D, and energy conservation equation and the species conservation equations. So basically, previous problem also we solved that. We saw that we need to know the kinetics of the reaction to to solve problems related to chemical reaction. So rate of reaction is need not be specified completely. So the reaction kinetics should be specified. And also option 3 it is given heat of the reaction. Heat of the reaction should be known so that we can use it in the heat transfer problem. So option 2 and 3 is the correct answer, that is option 4. Kinetics of the reaction like stoichiometric coefficients, order of reactions and constants in rate equation should be known along with the heat of the reaction. So answer is option 4. 2 and 3 should be known. So we'll see question 2. In question 2 it is asked that which of the following do we need to specify about the catalytic reaction? Activation energy, catalyst surface area and order of the reaction and reaction mechanism. So basically the options that are given for this problem are 1 only, 1 and 2, 1, 2 and 3, 1, 2, 3 and 4. So when we are dealing with this problem, what are all the things we need to specify about the chemical reaction? Activation energy should be known, that would only give the kinetics of the reaction, and catalyst surface area it is given in the problem, so that would also be helping in the problem solving. And order of the reaction, we should know the order of the reaction to solve the problem. That is what we saw in the previous problem solution. Stoichiometric coefficients, order of reactions, constants in the rate equation should be known. So activation energy, catalyst surface area and order of the reaction should be known. So answer to this problem is option 3. That is activation energy, catalyst surface area and order of the reaction should be known. Uh, no, so just a 5 minutes break. We'll start the session by 7:30. So yeah, sorry for the interruption. We'll start this remaining session. So basically, we were seeing question 3. How many mass conservation equations do we need to solve? So in this, it is like we'll be solving generally the governing equations, continuity equations, momentum conservation equations, and energy conservation equations. And since we are dealing with chemical reactions, we'll be using species conservation equations also. So let us consider that there are n number of species, and there is one continuity equations. So when all these species conservation equations are put together, we'll be getting the continuity equations. Continuity equations. So we need not solve for all the continuity. So we need not solve for all the continuity, all the mass species conservation equations. Species number of species minus one equation would be sufficient to solve for the mass conservation equations. Sorry, species conservation. So together with the continuity equation would give the n number of equations, where n is the number of species. So here it is like only 1, 2, 3, and 4. The number of mass conservation equations here would be like n number of equations, where the n is the number of species. So in this problem, it is the water gas shift reaction. So where there is two reactants, that is carbon monoxide and the water, giving carbon dioxide and the hydrogen. So putting together all those things, we'll be getting 4 species. Number of species in this case would be 4. So we are like the answer to this problem is 4. Number of species is 4. Continuity equation would be 1. Species conservation equation, therefore it is like ns minus 1, where ns is the number of species under consideration. So it is like 4 minus 1, 3. Total number of equations would be ns minus 1 plus 1, that is ns minus ns, where ns is the number of species, that is 4, and we'll be getting the 4. So answer to this problem is 4. Answer is 4. So we'll move on to next problem. Assuming the flow to be three-dimensional, total number of partial differential equations that needs to be solved is 5, 6, and option 3 it is 7, option 4 it is 8. If the flow is three-dimensional, we would be how many number of partial differential equations that needs to be solved. The number one would be continuity equation, and we would be needing mixture momentum equation, where it would be 3, because it is three-dimensional. We would be having all velocity fields u, v, and w. So it would be 3 momentum conservation equations, and again one energy conservation equation, and we'll be getting the species conservation equation. In species conservation equation, it would be ns minus 1, where ns is the number of species. So we'll be getting ns minus 1, that is 4 minus 1, 3. So one continuity equation, 1 plus 3 momentum conservation equation, 4, and energy equation 5 plus 3 species conservation equation. So the answer to this problem is 8. It is 8. So the continuity equation is 1, momentum conservation equation is 3, energy conservation equation is 1, species conservation equation is number would be 4, but we would be subtracting 1 that is needed to be solved. So it would be 3. So the total would be 1 plus 3 plus 1 plus 3, and that is 8. Total would be 8. 1 plus 3 plus 1 plus 3 is equal to 8. So like in general, it is like we are having 8 equations. So we'll be having, can anyone say number of unknowns that will be present from these like when they are solving the equations, and what would they be? So yeah, we would be having 8 equations in the previous questions. The number of unknowns, if we take the list, it would be like um, 3 velocities we would be having in 3 different directions, like u, v, and w. And we would be having one pressure term and one temperature term in the momentum conservation equation and the energy conservation equations. And in the species conservation equations, we would be having the mass fraction term. So the mass fraction terms would be present for each of the species. But when it is like if it everything is added together, we'll be getting one. That would be one less the number of species present. So basically 3 velocities we would be having u, v, and w plus one pressure plus one temperature. This would give a pi, and mass fraction terms, that is like 4 species are present and we will be having 3. So basically 5 plus 3 we will be having 8. So 8 number of equations and 8 number of unknowns it can be solved. So we'll move on to question 4. Sorry. Uh, yeah, we have solved the question 4 where we saw that 8 equations would be present and we would be having 8 unknowns. So we'll go to the question 5, the last question from this session. The rate of the reaction term appears in which of the following conservation equations? So the option 1 is, I mean, they have given 4 options. It is like the first one is species conservation equation, and the next one is mixture mass conservation equation, and the next one is mixture momentum conservation equations, and the next one is mixture energy conservation equations. So what are all, in which of all these reactions the rate of the reaction term appears? It is question 5, it is 1 only. Option 2 it is 1 and 4. Option 3 it is 2 and 3. Option 4 it is 1, 2 and 1, 2, 3 and 4. So the answer is actually it appears in the species conservation equations and the mixture energy conservation equation, that is 1 and 4. So we'll see how and when the rate of the reaction term appears in these conservation equations. So basically the governing equation is given for continuity equation, where it is dou rho by dou t plus del dot rho u is equal to 0. And momentum conservation equation, it is dou u by dou t plus del dot u is equal to nu, that is a kinematic viscosity, into times del dot del u plus g minus 1 by rho times del p. And then it is energy conservation equation, dou t by dou t plus del dot ut is equal to k by rho cp into del dot del t plus mu by rho cp into phi v plus qr by rho cp. And last one is species conservation equation, where it is dou times rho y rho into yi plus yi by dou t plus del dot rho into u into yi is equal to del dot gamma times del yi plus si. This is the species conservation equation. Here rho is the mixture density and u is the velocity of the flowing fluid, and nu is the kinematic viscosity, g is the gravitational force, and p is the pressure force, and t is the temperature of the system, and k is the thermal conductivity, and rho again cp is the specific heat capacity, and mu is the viscosity, and phi v is the viscous dissipation term that we saw earlier also. Whereas if it is a low like inviscid flows, it could be neglected. And QR, it is the heat generated in the system or depleted, depends on the system. And it is yi, it is the mass fraction of the species. And gamma is the diffusion term for during mass conservation, and SI is the mass generated, or I mean rate of formation of the species. So these are all the governing equations. So basically the question that was asked was rate of reaction term appears in which of the following conservation equations. So they have given like mass conservation, momentum conservation, energy conservation, and species conservation. So in mass conservation, rate of reaction term does not appear. So in continuity equation, it is not appearing. So when we are looking at the momentum conservation equation also, only U and gravitational pressure forces are present. Rate of reaction is not present in momentum conservation equation also. And then when we are looking at the energy conservation equation, we are additional terms that have that we are getting is temperature, thermal conductivity. All these does not involve the rate of the reaction. And 5e, that is viscous dissipation. One more term that is extra present is QR by rho Cp, where QR is the heat generated in the system. So when would heat be generated in the system? Because of any chemical reaction that is taking place. So we need to identify what are all the things that are present in the QR. And coming back for species conservation equations, it is rho times rho yi. I mean, we are having mass fraction terms, and additional term that is present is Si, that is the rate of formation of a species. We also need to look further into Si and QR to determine which of these following terms are having rate of reaction. So Si is nothing but Wi into A. Like if consider a reaction where A P is the stoichiometric constant of the products, and AR is the stoichiometric coefficients of the reactants. So if it is like ARij plus, I mean we'll keep it like okay, if it is like ARij time xi, it is giving, I mean AR1j. Okay, times x1 plus AR2j times x2. It is together with more reactants, let us consider it is giving a product AP. It is one, I'm sorry, it is one AP 1j x 1 plus AP2j x2, and so on, like where x1 x2 are the species, and arj apj are all the coefficients. Consider we are having this equation. So this species rate of formation of the species is given by for each individual species, it is like rate of the reaction times the stoichiometric coefficients of the products minus stoichiometric coefficients of the reaction, I mean reactants, times the rate of reaction for multiplied by the molecular weight of that compound would give the rate of formation of that species I. So in this term we can say that rate of the reaction comes into picture. And also like another term that we kept for consideration is QR, where QR is given by the stoichiometric coefficients of the products minus stoichiometric coefficients of the reactants when we are subtracting and multiplied by the heat of formation of that species I. It would give the multiplied by the Rj, that is rate of reaction, would give us the QR. In general, the rate of the reaction is given by this KFI times the concentration of that species power to the Aij like coefficients minus Kbj power, this is concentration of the species to the power, where F and B are the forward and the backward reactions. So in general these are all the Arrhenius coefficients. I mean reaction rate is expressed in terms of Arrhenius coefficients, where it is in turn represented in terms of as a product of temperature, pre-exponential factor and activation energy E and exponential factor EA and so on. So this Arrhenius coefficient would in turn be represented by using all these activation energy, temperature exponent and pre-exponential factor. So basically what it could be understood from this is that the rate of formation of the species is having the rate of reaction, and also the rate of heat generation in the system is having the rate of the reaction. So which appears, SI appears in the species balance reaction equation and QR appears in the energy conservation equation, QR and SI. So basically the energy conservation equation and the species conservation equation both are having the reaction rate of reaction term. So the rate of reaction term appears in which of the following conservation equations? So it is species conservation and mixture energy conservation equation. So the answer is 1 and 4. So answer to this is option 2, that is 1 and 4. Uh, so yeah, that's all. That's all. These are all the problems for today's session. So if anyone is having any doubts, please let me know. If there is no doubts, we'll just look. Uh, we'll just have a quick recap of what we saw in today's session. So we'll wait 2 more minutes, and if no one is having doubts, we'll start the recap and we'll wind up today's session. So basically in today's session we saw week 4 assignment problems and week 4 practice problems. So for assignment problems, the first case was such that a catalytic reaction was taking place with inside the reactor having dimensions L cross W cross H, where L is the dimension along this, the length is very much bigger than the width along this direction, and which is in turn very much greater than the height. So plane B and C, B is the middle plane that is between A and D. It is exactly the midpoint, where plane C is at the exact midpoint between planes B and D. So in between the planes B and C, the catalyst is coated at the bottom walls. The reactor is either preheated or cooled through the top and the bottom walls between planes A and B. Depending on the requirement or the condition that is specified, it is either preheated or cooled, and that is the case for the assignment problem. The same water gas shift reaction where carbon monoxide and water reacts to give carbon dioxide and hydrogen. The reaction is mildly exothermic and is carried out in the targeted temperature range based on desired output composition. So these are all the things that is mentioned. So we need to identify how much of the carbon monoxide coming through the inlet gets converted to the carbon dioxide by using the CFD simulation. If this flow is steady and laminar flow, the following things questions need to be answered. So for that, this problem basically involves continuity equation and momentum conservation equation, energy conservation equations, and species conservation equation. Basically, when we are doing any things with chemical reaction in CFD, normally we use continuity equations and momentum conservation equations in general. So since this problem also requires heat transfer, energy conservation equation is also included in this. Along with that, chemical reaction is producing some species, or some species is getting converted to products. So we need to include the species conservation equation also. All these are based on mixture theory. I mean, like we are using mixture conservation, momentum conservation, and mixture energy conservation, and mixture continuity equation. The thing to be noted here is when considering the mass conservation, the continuity equation and the species conservation equation, when all species conservation equation is put together, we will be getting the continuity equation. So the number of species conservation equation that needs to be solved is one less than the number of species present in the system. So these were the basics that was covered in this problem, and the problems that were asked included questions that were included in this were like how many number of equations that needs to be solved, and the temperature profile, how it would be. Basically, the system is exothermic, so heat would be produced. Mostly the reaction takes place between planes B and C. If the temperature is, if the reactants are at a lower temperature, so what would be the case is they are preheated. So if the system is if the reactant gas is preheated and it is sent inside, so what would be the thing? Initially it would be increasing till planes B and C, it would be increasing, after which it would remain constant. So these were all the questions that were covered in this session. In this assignment problems, like number of mass conservation equation that was asked, and what are all things that would be specified for the chemical reaction when considering chemical reaction in CFD. Those would be the kinetics of the reaction is very important, and it needs to be included in the equations. So the kinetics of the reaction rate needs to be specified, and how the temperature thermal boundary conditions, it could be Dirichlet or Newman, where we can either specify the variables or we can specify the flux values. And also the concentration was asked, where between plane B and C it was only catalyst that was is placed. So at the bottom, the carbon monoxide species concentration would be 0. And this was the question: temperature increases up to plane C and then remains constant when if the reactant enters at a lower temperature than the targeted temperature, so that we would be heating up the reactants. And we also saw when viscous dissipation term would be neglected in the energy conservation from the energy conservation equation. It would be neglected when we are using inviscid flows, where inviscid flows are nothing but where viscosity effects are not negligible. Most real life problems when heat fluxes are strong and the temperature variation is because of the flow velocity. In those cases, we would be neglecting the viscous dissipation energy. In other cases, when highly viscous liquids are considered, and in those things, uh, additional forces would be included, and also the local increase in the temperature, it would be having a majority effect in the viscosity. Thereby, the viscous dissipation effect should be included when we are dealing with highly viscous fluids systems. And also we saw how convective heat transfer equations are included in the Navier-Stokes, energy balance equations that we solve along with the Navier-Stokes equation. And also we saw how the well posedness and means we should be having a unique solution, and the solution should be very responsive to the changes in the initial and the boundary conditions. And also we saw the elliptic, hyperbolic and the parabolic equations, and how their region of influence would be there, and the region of dependence would be influencing the region of influence, and how the boundary conditions should be chosen for different different equations. And also we saw the practice problems. In this also it was given the water gas shift reaction, and in this water gas shift reaction a few conditions were given. Based on that we were solving number of what basically these were kind of same, asking what needs to be specified when considering chemical reaction, where the reaction kinetics plays a major role along with the heat of the reaction. And also what are all the things need to be specified when considering catalytic reaction, like activation energy, catalyst surface area, and order of the reaction. All these things needs to be specified. And how many mass conservation equations would be there? That would be ns, and that is number of species, and the number of partial differential equation that needs to be solved considering all the continuity, momentum conservation and the energy transfer equations, and the species conservation equation. And this is an extension which was asking where the rate of reaction term appears, and we identify it to be the species conservation and the energy conservation equations. So that's all for today's session. Well, I thank you for attending today's session. If there is no doubts, we'll close the session, and in the next week we'll solve the problems from the next assignment, and we will see how to solve those problems. So thank you for attending today's session. If there is no questions, we'll close today's session. Thank you for attending.